Okay, a number of things that you're going to hear in today's slides are a little repetitive from some things yesterday and the day before, but this I think will nicely round out kind of what's going on with vector functions, which you'll see sort of the story seems to stop and we don't really pick it up again for a little while. So the next time around, we will be looking at functions where there are multiple inputs required. So something like, so right now you can imagine what we've been looking at, this R of t, you feed in a single number t, and then you get an x, y, and a z out, right? The things that we're about to look at, for instance, are going to be like z equals f of x, y. So we'll be taking a break from this sort of as a topic, but I think this day will help round out kind of what's going on here, right? The whole point is vector functions again are just like parameterization. They both model motion in space. So there's some things that we should talk about in that framework, and then we will come back to some of these ideas in the final chapter. So what's coming up? Again, we're just finishing off chapter 13 with this. Chapter 14 will be functions where there's multiple inputs instead of what we've been looking at in this chapter where there's multiple outputs. In multiple outputs just meaning multiple real numbers all stuck together in a vector. Chapter 15 is going to be integration of the type of functions introduced in chapter 14. And chapter 16 will actually be new versions of the fundamental theorem of calculus for those types of functions. We will actually see, I think, 4, 5, maybe 6 types of theorems that are all basically the fundamental theorem of calculus in the final chapter. Okay, so in the first physics class, there's this overly simplistic view that all motion is described as occurring on a straight line. Of course, the usual other things in a vacuum, no friction, none of that, right? But it's a good model, right? It's close enough. Like you got to start somewhere. But the thing is, motion just not very much motion occurs in straight lines, right? Like there are no straight lines anyway. Um, Look, now that we have vector functions, which again encode the same information as a parameterization does, essentially, and describes a motion in three-dimensional space, what we can do is now describe some of the basic physics that occurs in 3D space. That's better than just assuming that all motion occurs along one axis, like just along the x-axis. So what we should just say here is, given three scalar functions, three functions in the sense of an algebra class or a calc 1 class, let's call them f of t, g of t, and h of t. We have parameterization, right? At a moment t, you get that the object is located at a point, f of t, comma g of t, comma h of t, round parentheses. The vector function version is that for an input t, the vector function gives the output and it gives you a vector. So again, there's this pass back and forth between points and vectors for parameterization versus vector function. But they're really, again, it's encoding essentially the same information in technically different objects, whether it's a point or a vector. Again, here, there's nothing that's all that fancy, right? So the F formula describes the X value. The G formula describes the Y value. The H formula describes the Z value. Again, all of these at a specific moment in time t. And do you have a point or do you have a vector, right? So let's just mention that there's an actual application of all of this vector functions or parameterization stuff in planetary motion. And here's the thing, in Calc 1, here's how motion works, right? So in Calc 1, we have an x-axis and a y-axis only, though when we start doing physics applications, we tend to replace the x or the t, yeah? But then the motion that occurs along a straight line, if f of t describes a position, you could almost imagine, even if the motion happens horizontally, we just sort of say that the motion happens vertically along the y-axis. Even if it's not actually vertical, it just matches the picture that we would draw. And then, you have velocity, right? So velocity, is a derivative of position. It's given by technically this limit-based definition. That's the velocity at time t, right? And then you know that if you take this velocity, which is signed, and you take the absolute value, you get the speed. And acceleration is the second derivative of the position, or the first derivative of velocity. All things you know from Calc 1, you know these very well. Now, in Calc 3, we have 2D and 3D motion described by a vector function. So here's a little review from 2 days ago, that if you have a vector function, and let's say that describes the position of an object moving in 2D space or 3D space, the derivative, which is itself a vector function is the velocity vector. The we can't say absolute value now because we have a vector. So the magnitude of this is going to be the speed. It is a scalar. And then finally, the derivative of the velocity vector function is the acceleration vector function.